Hi, welcome to Astro Night. We're gonna get started in just a second. So thanks everyone for coming to Berkeley Astro Night. Today we're gonna have Emmanual Schaan give us our lovely talk on a cosmic shadow theater. Emmanuel is a researcher at the Berkeley National Laboratory. As a cosmologist, he studies the origin and evolution of the universe by analyzing data from large telescopes in the US, Chile, and space. His goal is to learn about the nature of dark matter, dark energy, and the masses of neutrinos by using the universe as a laboratory. His work focuses on the cosmic microwave background, the earliest light visible after the Big Bang, and the large-scale distribution of galaxies and matter in the universe. Emmanuel grew up in Paris, France, before moving to Princeton, New Jersey, and then Berkeley, California. He loves astrophotography, sailing, tinkering, electronics, and DIY projects. Thanks again for coming.
Good. Thanks so much. Can everyone hear me? Great. Thanks a lot, Natasha, for this introduction, and thank you everyone for joining us tonight for this other session of the Astro Night. And I'm really delighted to be able to tell you about astrophysics and especially about my research. So you may know that the stargazing afterwards has been canceled because of clouds. That's tough luck, but that means you might have more time for your questions and grilling me at the end of this talk if you're interested in and you want to stay. So the topic of this talk, a cosmic shadow theater, really is about looking at the shadows of galaxies. And so what's a galaxy shadow? So you may be familiar with what galaxies are, and I'll tell you much more about them in a moment. But if you want to see a galaxy shadow and what you have is a galaxy, really all you have to do is hold that galaxy between two fingers and place it in front of the light. And this may sound impossible, but these galaxy shadows are actually one of the most powerful ways to learn about galaxies because they reveal some of the invisible components of galaxies. And so this will be the topic of this talk, these galaxy shadows. And the picture I'm going to try to paint for you tonight is that the observable universe really is a shadow theater in which galaxies are the protagonists and in which the backlight is the very first light from the Big Bang, the cosmic microwave background. So hopefully that'll be interesting. But before moving on, I just wanted to say a few words about why I'm really delighted to be here and to tell you about my research. And in part, this is because in the room, there's a number of amateur astronomers, I'm sure, or aspiring amateur astronomers. And I just wanted to highlight how important amateur astronomers actually are to astrophysics and to science in general. And so I just wanted to highlight two pieces of work from amateur astronomers that actually sort of push the state of the art of astrophysics. The first one, this person, Donald Brunts, during the 2017 solar eclipse, made the very most precise measurement to date of gravitational lensing by the sun. And I'll tell you about gravitational lensing in a moment. I also wanted to highlight how every day amateur astronomers actually discover comets that we can then follow up on. So a big thanks to all the amateur astronomers or people who might be interested in becoming ones in the audience tonight. And in the same line of thought, I just wanted to highlight that all of astrophysics research that is done here at Berkeley and really pretty much everywhere in the world is publicly available online on these two websites, archive.org and the NASA Astrophysics Data System. So if you Google any of these, archive.org or NASA Astrophysics Data System, you can find all of astrophysics. And in particular, all the results that I'm going to present to you tonight are on these websites. They were publicly funded, and naturally, the results are publicly available. And last thing I wanted to say about maybe encouraging you to go out there and stargazing, although not tonight, is all the things you can do with amateur astronomy. You can build your own planetarium out of a tin can. You can build your own tracking mount to do long exposures. There's a number of astronomy clubs around here. And in Oakland, there's the Chabot Space Science Center, where you can go and learn to build your own telescope and your own telescope there. So if you're interested in any of this, don't hesitate to Google my name, and you'll find it on my website. But back to tonight's story, that cosmic shadow theater. And again, as I mentioned, this is a story where the universe is the shadow theater. The protagonists, the hands, are galaxies. The backlight is the very first light from the Big Bang, this cosmic microwave background. And the shadow that you get to see from this backlight may tell a more interesting story than the galaxy itself did. So I'll tell you first about the protagonists, the galaxies. Then I'll tell you about the backlight, that cosmic microwave background. And then I'll tell you the story of these shadows. So let's get started. Protagonists, galaxies. And to talk about galaxies, it helps to get some perspective and to start from down here on Earth and slowly zoom out and get out of our own Milky Way. So let's do this. Here's a photo I took about a 5-hour drive from here at the Lassen Volcanic Park. And pretty much every dot you see in this image is a star, except for Jupiter and Saturn. But otherwise, every other dot is a star and is a star inside our own galaxy, which is called the Milky Way. And you can see it through this very big band, which is how the Milky Way disk looks like from our vantage point on Earth. Now, if you could actually escape our galaxy and look at it from the outside, it might look something like this. So a beautiful spiral galaxy with a bar at the center. And the sun, our star, the star that we're orbiting around, is somewhere in one of these arms. And so the sun, our star, really is only one of about 100 billion stars in our galaxy, the Milky Way. Now, the Milky Way, our galaxy, is not the only galaxy in the universe. And I just want to, if you see on my slides a little heart like this, this means there's something you can remember by heart on this slide. Something like 100 billion stars inside the Milky Way, which is our own galaxy. So again, the Milky Way is not the only galaxy out there. Here's one of our nearest neighbors, the Andromeda galaxy, another beautiful galaxy. And in fact, if you look out in space, what you see is many, many, many more galaxies. So this is the so-called Hubble Ultra Deep Field, where the Hubble telescope stared at a tiny patch of the sky that had no visible star for a very long time. And pretty much every speck of light that you see in this field of view is an individual galaxy. Now, an image like this one allows you to estimate how many galaxies there are in the whole observable universe, if you were to look in all directions as opposed to just this tiny patch of the sky. And the number comes out the same, about 100 billion. And so I should remember that our universe contains, the observable universe contains about 100 billion galaxies, in each of them about 100 billion stars, and the sun, our star, is just one of them. Okay. This is this image from the Hubble Space Telescope, which tells us about all these galaxies. But in fact, it may look like a flat 2D image, but in reality, we actually know the distance to many of these galaxies through something called redshift. And because light takes some time to travel from the galaxy to us, the galaxies that are farther, you see them longer ago. So really, this 2D image is a 3D image because you know the distances. And this 3D image really is a video because there's time information. The stuff that's farther away, you see it a longer time ago. And so what you can do actually is step through this 3D image or this 3D video and look at all these many, many galaxies. And as a physicist, when you see all these galaxies, all these specks of light in space, the first question you ask yourself is that of dynamics, or how is this system evolving in time? How are these galaxies moving? And this is a question that has been answered observationally, and the answer can be visualized in this way. So here in the simulation, every galaxy has been replaced by a dot or sphere that represents its position. And if you play this simulation forward, what you see is that all these big dots, these big galaxies, as time moves on, move farther and farther away from each other. And this fact, which is an observational fact, and the fact that these galaxies have been measured to move away from each other, is what we mean when we say that the universe is extended. Okay. So this is about all I wanted to say about these protagonists, these galaxies. And so here's a summary for you to remember. The Milky Way is our own galaxy. It is one of 100 billion galaxies in the observable universe. And each of these galaxies contains around 100 billion stars. And these galaxies are all moving away from each other, which is what we mean when we say the universe is expanding. So what I'd like to do now is to give you all 1 minute to look at this slide and try to remember what's on it. And then I'll ask you to be able to remember it. So you have 1 minute to look at the slide. So sorry. All right, so time is up. So I would like you to turn to your neighbor, and with the help of your neighbor, remember what was on this slide and try to discuss it. You have 2 more minutes. All right, so time is up. So let's time to return. And hopefully you were able to remember these points. And the key one that will come in handy in just a second is the last one, the universe is expanding. So keep that in mind. And also remember this Milky Way and this Andromeda galaxy are neighbors, they'll come back in the story. But okay, these were the protagonists, the galaxies, protagonists in this cosmic shadow theater. Let's now talk about the backlight, this cosmic microwave background. So what does this all mean? Well, if you remember what we just said, the universe is expanding. So what that means is that if you go back in time, the universe contracts, right? So as you go forward, the universe expands. If you go back in time, it contracts. And if the universe was more contracted or smaller in the past, that means it was denser. And as you may know, when you compress things, when you make them denser, they get hotter. And this is something you might have experienced if you've ever pumped up a bike, that the pump gets hot. And so the consequence of this is that the universe back in time, not only was it denser, it also was hotter. And this is what we mean when we talk about the hot Big Bang model. We're not so much talking about a possible singularity or time zero. Really what we mean is that earlier in time, the universe was denser and hotter. Okay, first point, the universe was hot. Another thing that you might know about stuff that's hot is that hot things glow. And that applies to really anything that is hot. All of our bodies are warm, and so they glow in the infrared. If you heat up a piece of metal to work on it, you might glow red in the red part of the visible spectrum. If you heat it up further, like in an incandescent light bulb, it glows more and more yellow. And if you heat it up even further, like something like the sun, you might see this sort of white color that the sun is. So you probably see where I'm going with this, but there's these two facts. The universe was hotter and hot things glow. So the consequence of this is that we should be able to see the glow from the early universe when it was hot and dense. We should be able to see this leftover heat from the Big Bang, this afterglow from the Big Bang in the form of some relic light, some radiation. And this light is what we refer to when we talk about the cosmic microwave background. So cosmic microwave background, cosmic means that it comes from space and not a single source. It comes from outer space, cosmic, outside of the Milky Way. Microwave, just because today it happens to be in the microwave frequency when we observe it. And I'll tell you more about this. and background because the whole universe was hot. So the whole universe was glowing. It was not just a single source that was bright. It was a background that came from all directions. It was diffused. And so this is what we call the cosmic microwave background, or the CMB in short. So the CMB was sort of predicted and detected in the same issue of the same journal, predicted by people like Jim Peebles and collaborator, and detected at Bell Labs by Penzias and Wilson. And this discovery was really important for our understanding of the universe in a number of ways. And let me tell you about this right now. When you measure this light from the Big Bang, as a physicist, the first thing you ask is, what does this light look like? You put a prism in front of it, and you ask, is it red, is it blue? What kind of frequency? This is what we call the spectrum. So as a function of the frequency of light, how much light do you have? And this curve that was measured from the cosmic microwave background may not mean much to you, but it's a very important curve in physics. It's called black body radiation. And this is the radiation you expect from anything that's hot. So again, people, hot metal, incandescent light bulb, the sun. And so the fact that the CMB, the cosmic microwave background, has this exact spectrum really means that it is the radiation from something that was hot and in thermal equilibrium, which is the early universe. So this is a really important fact. It tells us that the universe was indeed hot, as we expect from the fact that it's now expanding, and that it was in thermal equilibrium. And this is perhaps the strongest evidence that we have for this so-called hot Big Bang model that I told you about. So the fact that indeed the universe was denser, hotter, and we do see the glow from that. And if somebody asks you, after this talk, how does the cosmic microwave background support the Big Bang model? What you can tell them is the following. If you've ever sat in the subway or in the bar on a chair that looked like it was empty, but you sit on it and you feel that warmth, you do know that somebody has been sitting there before. And this is basically the cosmic microwave background. So I can't quite see the early universe, but I see this leftover heat, the fact that the universe wasn't really hot right now. Okay, so this is the cosmic microwave background, how it tells us about the hot Big Bang model. Now, I said it was a background, and it came from all directions because the whole universe was hot and emitting it. So you might want to look at a map of it, look in all possible directions and see what it looks like. And this is what it looks like. So the color here indicates the temperature of that early universe. And as you can see, it's basically the same in all possible directions. So kind of boring. But this is also what thermal equilibrium looks like. And you can think of this as the baby picture of our universe. So when you look at the cosmic microwave background at this boring uniform map, what you see is the universe the way it was early after the Big Bang. But you can do better than this. You can do better than this if the precision of your instrument is sufficient to detect changes in that temperature, to above absolute zero. And if you can measure changes that are about a few parts per million, the map looks much more interesting. And this is what you see. So there's two things that should strike you. The first one is this bright red band at the center. And what this band is really is the Milky Way arrow galaxy. So if you remember that stripe of star in the night sky, in the microwave, this is what it looks like. It's a very bright stripe. And this is the Milky Way arrow galaxy. So this is not the signal I'm interested in. I want to look at the early universe. Instead, I'll look here and there. And what you see are those red and blue spots, those hot and cold spots in the cosmic microwave background. And what they show you, again, is the baby picture of the universe. They tell you that in this particular direction, the universe was hotter, and in this particular direction, it was colder. And so this tells you about parts of the universe where it was denser or less dense. There's so much more I could tell you about the cosmic microwave background. In my opinion, it's probably the coolest thing in astrophysics, and perhaps in all of physics altogether. This could be many, many talks, but for today, I need to leave it there. And so this is the summary for this cosmic microwave background. So again, the universe is expanding as time moves forward. And so when you go back, the universe is instead contracting getting denser. When you compress things, they get hotter. This is the hot Big Bang model. Now, because we do see the fact that hot things glow, we actually see the leftover heat from the Big Bang, that cosmic microwave background. It supports the hot Big Bang model, just like a warm subway seat tells you that somebody was there before you. And its magical black body spectrum tells you that the universe indeed was in turmoil. So again, I'll give you 1 minute to look at this slide, try to remember it, and then I'll ask you to discuss it with your team.
Yeah, so different all the stars
All right, time to discuss it. All right, time is up. So let's bring it back here. So I hope you were able to remember some of this. I'm sure there were points here that were confusing and that raised some questions. And so I'd ask you to keep those questions in mind. Don't forget about them. And this way, at the end of the talk, you can ask them and they get them clarified. So CMB, reading light from the Big Bang, supports the hot Big Bang model, tells us a whole lot of things, but really for the purpose of this talk, we won't care too much about it other than the fact that it is a light. And so putting it together, this is the picture. Here's the sun, the star that we are orbiting right now. And around it are neighboring stars in the Milky Way. And as I zoom out, I see more and more of the stars in the Milky Way. Finally, I see the Milky Way galaxy itself, some of its neighbors, more and more of its neighbors. And if I keep going far enough, I'll reach the end of the observable universe. And what I see is this cosmic microwave background. So please don't be alarmed by this butterfly shape. It's not that there are no galaxies here and there are plenty there. It's just we only looked in those directions. But that'd be really interesting if that was true, though. But so this is the picture, right? You are here at the center, not because we're special in any way, just because obviously our observable universe is centered around us, because I can look to the left, I can look to the right, I am somewhat in the middle. But the important part here is you have all of these galaxies in the observable universe, about 100 billion of them. And you have this light that comes from a long time ago, the cosmic microwave background. And for this light to travel all the way to us, for us to see it, as it travels, it might hit those galaxies. And so this is where galaxy shadows are going to come in. But before I tell you more about these galaxy shadows, I just wanted to motivate why you would want to look at galaxies in this way. Why not just look at the galaxy directly? Why would you want to look at its shadow? And the reason why is the following. The fact that we like to say in astrophysics that light is a biased tracer of the mass. Meaning that if you look at the light from stars and galaxies, it actually does not give you a very good picture of where the mass is. It gives you a biased picture. And to understand this, here's an analogy. If instead of looking out into space, you were to look down on Earth at night, what you see are these dots of lights, which come from lighting in the cities. And so you might ask yourself, if you were an alien, where do people live on this planet? And if this is all the information you have, you might say, well, presumably this light was made by people, so where there's more light, there's going to be more people. And so that could be your guess, and that wouldn't be a bad guess. This is the image of population density in the world. So if you compare the two, it's not too bad. Indeed, where there's a lot of lights, there's usually people. But it's not perfect. For example, you can see that light is very concentrated in dots, whereas population is much more diffuse. And there are places where you might not see much light, but there's actually a lot of people. And the reason for this is simple, is that light does not tell you where people are, it tells you where cities are. And people don't necessarily live in cities. So in that respect, light is a biased tracer of population. Well, in galaxies, the same is true. When you look at the light from the stars in the galaxies, it does not tell you the whole story of where the mass is. And so here's an illustration of this. If you take a galaxy and you backlight it with this cosmic microwave background, so again, the cosmic microwave background travels all the way to you, but hits a galaxy. This is what you might see. So again, this is a galaxy the way you see it if you just look at it, if you look at its starlight. But if you were to instead look at its shadow on the cosmic microwave background, this is what you might see. And in this image, the dark blob you see here is the shadow of the gas around the galaxy. And so even though this galaxy is a tiny little blip on the screen, there's actually a ton of gas around it. And in fact, more than 90% of the ordinary matter in the universe is not in the form of stars, it's in the form of the gas that's hidden around galaxies. If you just looked at the galaxy, you would be missing 90% of the ordinary matter. Now, there's different types of shadows on the CMB that you can look at. And so these were shadows of the gas, but I'll also show you shadows of the mass, and I'll tell you what that means. But these special shadows do the following. So here's an image of the cosmic microwave background behind the galaxy. But because there's mass associated with this galaxy, the cosmic microwave background ends up looking like this. So if I flip between the two, and I'll tell you much more about how that works in a moment. But this effect tells you about all the mass that's around the galaxy, that's not just in the stars. And so I told you that 90% of the ordinary matter was not in stars, it was in gas. Well, there's this other type of matter that we call dark matter that's actually 5 times more abundant than all the ordinary matter in the gas and the stars. And you wouldn't know about this if you just looked at the galaxy, but you know about this once you look at these shadows. So, so this is the story of this cosmic shadow theater, revealing the invisible properties of the galaxies, like you would a watermark on a dollar bill by placing it in front of light. So how do you measure these shadows? Well, you need to make very precise images of this cosmic microwave background in order to see the shadows. And to do this, we use a number of telescopes. So I'm part of this Atacama Small G telescope collaboration. And this telescope sits on top of a very high plateau in the Atacama Desert in Chile at a very high altitude, which is helpful because there the sky is very, very dry, and that helps you look in the microwave. So if we go see the telescope, we'll see what it actually looks like. And you can see that on this plateau, there's a bunch of equipment. And behind this ground screen here is the Atacama Small G telescope. The Atacama Small G telescope has some neighbors called Science Array, Class, and a new big neighbor coming soon that I'll tell you about in a moment. For the aficionados in the room, this is what the telescope looks like. Don't worry if this means nothing to you, but basically hidden behind this screen is a big telescope with a primary mirror, a secondary mirror, and a detector in there. It's an off-axis Gregorian, if that means anything to you. But this is the ACT collaboration. To collect this data, to analyze it, and to interpret it takes a lot of people. And so this is, this might be the last photo we took at an in-person collaboration meeting before COVID. But using data from this telescope and working with all these people, we're able to extract those gas shadows and those mass shadows. So let me show you how that works. Let's start with those gas shadows. And maybe I should tell you what I mean by gas shadow. And what I mean really is something called scattering. And scattering is something you see every day. So when you're outside, how do you know that there's gas in the atmosphere? How do you know that there's gas around you? Well, of course, you're able to breathe, so that's a clue. But how can you see it? And the way you can see it is that if you look up at the sky, it's blue. And if you look up towards the sunset or sunrise, it's orange. And all of these colors, blue, orange, are the result of a backlight, the light from the sun, interacting with the gas. And so in the same way that we can see the gas through this sunrise and sunset, the same way we see those gas shadows on the cosmic microwave background, except there it's not the sun that's rising or setting, it's the cosmic microwave background. That's first light from the Big Bang. And it's not setting on our Earth, it's setting around a distant galaxy. So let's do this, let's look at those gas shadows. And so what you can do is you can simply look at a galaxy that you know and you might have seen through its starlight. And you can point your telescope there and try to find the shadow. And if you do, what you find is that this galaxy might fit within the central pixel of this cosmic microwave background map. And the map, when you look at it, basically, there's nothing to see. It's just noise. And so that's too bad. The shadow is too faint for us to see. When you look at the position of that galaxy, which is in this central pixel, there's nothing to see. So you could just stop there and say, this sounded great, but turns out it was a bad idea. There's nothing to be seen there. But instead, what you can do is use the fact that we know of way more than one galaxy in the universe. And so when you need a lot of galaxies, what you do is you ask the BOSS, the Baryon Oscillation Spectroscopic Survey. Doesn't matter what that means. What it is a telescope that has collected the 3D positions of many, many galaxies. And so you are here in the universe. Each dot here is a galaxy measured by this telescope. Again, there's only galaxies in these two portions of the sky because we've only looked there. Presumably there would be galaxies here and there. But when you have all of these galaxies, something like 400,000 of them, you can do something that amateur astronomers know and do very often. You can combine the signal from each of these galaxies. You can combine the undetected shadows from each of these galaxies and combine them into a detection. And this is what it looks like. So in this image of the cosmic microwave background, I'm going to be adding more and more galaxies. And hopefully the shadow will start to appear. So as you add more and more of these galaxies, the noise averages down. And finally, the dark blob appears. And so again, while the galaxy fits within the very central pixel of this map, there's actually gas to be seen much farther out. So this is the shadow of the gas. And to put this into perspective, something you can go out there at night and see. In this image, you might recognize the band of the Milky Way. And this dot here is the Andromeda galaxy that I showed you before. And here in purple is what you could see if your eyes could see that shadow of the gas. And so if you just went out there stargazing at night, you would see the Milky Way, you would see the Andromeda galaxy, but instead of being just a very small blip of light that you can see with binoculars, it would cover 60 degrees of the sky, just the gas around the Andromeda galaxy. Okay. So the Milky Way, the Andromeda galaxy. So this is all I wanted to tell you about these gas shadows. Now I want to tell you about these different types of shadows, those mass shadows. And again, why when you have a galaxy with mass around it, the cosmic microwave background appears distorted in a way that tells you about the mass. So this effect is called gravitational lensing. And it's the fact that every massive object, and that to some extent includes all of us, distorts the path of light. And so for us, because we're not very massive, this is not something you see. But for massive objects like galaxies, this effect becomes detectable. And so massive objects reflect the path of light, and this applies to the cosmic microwave background. In practice, this is something that you can simulate at home. If you have a glass of wine at hand, you can look at the effect of lensing. It looks very much like this. So you move your glass of wine in front of the picture of the cosmic microwave background, and you've done general relativity at home. And it works with anything. So I said it works with the cosmic microwave background. But if you download this app on your phone, GravLens, you can really gravitationally lens anything, including your children if they're being too young. But in practice, again, this effect is a very small effect, just like the gas shadow that I showed you a moment ago. Because in practice, here's an image of the cosmic microwave background without any gravitational lensing. So this is a simulation. And I can simulate the effects of gravitational lensing on this map. And this is what you get. This is the lensed map. So I'm going to flip between the two, unlensed, lens, unlensed, lens. This is the size of the effect. And of course, you only get to see the lensed map. So this seems difficult, and this seems pretty hopeless to be able to see the gravitational lensing of the cosmic microwave background. But again, just like the last time, you can combine the undetected signal from many, many, many galaxies in order to get a statistical detection. And what you do when you do it, this is what you get. So you probably remember the gas shadow that I showed you a moment ago. And this is the shadow of the mass. And so again, you can see that the mass is way more extended than the galaxy, which fits within the central pixel of this mass. And so this shadow theater gives you a much more complete picture of galaxies than just looking at the starlight. And this is why these shadows promise to tell us about how galaxies form and evolve in a way that we really can't learn otherwise. And looking towards the future, this is only the beginning. Those images are going to get much more precise and with much higher resolution. And this is thanks to a number of experiments which are coming online. The first one is called the Simons Observatory. So this is the new neighbor that's going to arrive on the Atacama Plateau, where the Atacama Cosmology Telescope is. And in particular, it will have a number of telescopes, small aperture ones and a large aperture one. And this is a picture of the collaboration meeting of Simons Observatory. Again, I think this was the last in-person one before COVID that was here at UC Berkeley. So this is really exciting. The telescopes are being built right now, and the first light should happen in 2023. So we'll have way better cosmic microwave background data to look at these galaxy shadows. And the other key improvement that makes it exciting to look at these galaxies right now is the Dark Energy Spectroscopic Instrument, or DESI. And this is an experiment in which UC Berkeley and the Lawrence Berkeley National Lab play a key leading role. And the images that you see here are photos that I took early 2020, again, right before COVID, during the commissioning of this instrument on this telescope. And what this instrument is going to give us is the position of not hundreds of thousands of galaxies, but tens of millions of them. And so this is a large improvement in the number of galaxies that we know about. And this translates directly into better detections of their shadows. So summary of this talk is the following. Hopefully you'll remember that in our observable universe, there are about 100 billion galaxies with 100 billion stars in each of them. That the universe is in expansion, meaning all these galaxies are moving away from each other. And as a result, if you go back in time, the universe was hot and dense, and we see the afterglow of this, the so-called cosmic microwave background. Now, this cosmic microwave background can be used as a backlight for all of those galaxies. And this backlight shows us a number of shadows, shadows of the gas and shadow of the mass, which give us a much more complete picture of the galaxies. And so I'll stop there. Thank you very much for the attention, and I'll be happy to take any questions you have.